Any questions about anything? Or anything from last time? So today I'm going to do some famous things about applications of this least upper bound property that I discussed last time, sort of the critical property of calculus and why everything works. There's multiple words for this least upper bound property. The least upper bound, I wrote LUB. But an equivalent word is supremum. Sup. And that sup stands for supremum. But the least upper bound is sort of the most descriptive word for soup. They're the same thing. And of course, the least upper bound property is equivalent to the greatest lower bound property, LUB property. It's not easy. You just take minus everything, and you'll see that same things apply to greatest lower bound, to GLB, which is greatest lower bound. Property. And the greatest lower bound, the fancy word for that is inf. Infimum. Okay, so that was the topic of last lecture. At the end last time, I discussed a little bit about the Archimedean property of the real numbers. Which says that given a real number R, I like to use R for real numbers. The book sometimes uses X or Y, but I like to use little r for just to emphasize that it's a real number. So given a real number R, you can find an integer that's bigger than it. It's like, big wow. But Archimedes realized you got to think about these things, and how would you demonstrate that in a way that makes sense to people? Turns out it's kind of a heavy concept, and it's related to the least upper bound property. I demonstrated the Archimedean property by deducing it from the least upper bound property last time. So it's not sort of a trivial thing, even though it sounds trivial. Given a real number R, there is a positive integer that's bigger. With n bigger than R. I guess the book likes to say bigger than or equal to. It doesn't really matter, because n plus 1 would be strictly bigger. Okay, that's it. And last time I showed that that the LUB property implies the Archimedean property. And the Archimedean property is sort of related to the fact that there's no biggest positive integer. So related to no biggest positive integer. Which also sounds like a no-brainer. Well, that's an easier thing to show because if n was the biggest one, then n plus 1 would be bigger. But it's a very similar thing. And Archimedes was thinking about that too. And of course, back then, a more interesting thing was to say was to figure out that there was no biggest prime number. So they were thinking about stuff like this. And then they started thinking about whether or not the square root of 2 was rational. So it very quickly escalated. And all of these things are kind of related when you get down to the fundamental business. Let's see, an important corollary of the Archimedean property well, n can get bigger and bigger. Well, guess what? 1 over n can get smaller and smaller. And so the fact is the infimum of the set of natural numbers 1 over n, such that n is a natural number, is equal to a big fat 0. Let me explain why that's true and how you can figure it out from the definitions. I'm going to try to do streamlined demonstrations of these things, so you should read the book carefully to make sure you swallow the book, the way the book does it. Let's see. Oh, let's call this set S. Capital S. Notice that S is bounded below by 0. It's bounded below by 0. So a set that's bounded below has a greatest lower bound. That's the greatest lower bound principle. Any set that's has a lower bound has to have a greatest lower bound. So S has an infimum. The greatest lower bound equals an inf. Let 1 over, what am I saying? Let R be that inf. Okay. Notice that since 0 is a lower bound and R is a greatest lower bound, R is the greatest one, bound, we see that R must be greater than or equal to 0. Let's see. Well, if it's bigger than 0, here's what we can do. If R were bigger than 0, then I could use the Archimedean property to get an n with, let's see, we got 0 less than R less than, I guess we have a less than or equal to n here. If I take n plus 1, I would get one. So I get an n with this strictly less than n, and so take n plus 1 if the R is equal to n in the Archimedean property. The book wanted to put a less than or equal to there for some reason. So I have to live with it. Maybe that's what Archimedes did. I don't know. Okay, now you think about what that means. When I start inverting things, that would mean 1 over n is less than 1 over r. And oops, that means that, what am I saying? Oh, that's not what I had to do. I messed up here. I want to get an n that's bigger than 1 over r. I would have realized I screwed up when I wrote this next thing. All right, 1 over r could be really small. 1 over r could be really big. But no matter how big it is, Archimedean property says there's an integer that's bigger. Okay, and then when you mess around with that inequality and invert it, that reverses the inequality, and I get 1 over n is less than 1 over r, which would be r. And that would show me that, oops, r is not even it's not a lower bound anymore. So that would be a contradiction. R is not even a lower bound, let alone the greatest lower bound. I'm sorry, what did I do? R is not a lower bound, and so that's a contradiction. Lightning bolt. And that means that contradiction. So let's see, what did I assume? I assumed, well, if r was bigger than 0, then I get this contradiction. So r has to be equal to 0. And that's the conclusion of the thing. The infimum is 0. R was the infimum of that set. So check. That's what we want to see. Questions about that? I'll be really careful in the first couple demonstrations, just so they make sense to you, and you can read the book. There's like a couple really simple corollaries of the Archimedean property that I need to write down before we can get rolling today. Another one is what I basically just did here. If r is bigger than 0, it's a real number. I guess I should say that. If r, I'll say it like this. If r is a positive real number, then there is an n such that 1 over n is less than r. Similar to it sounds very similar to the Archimedean property. And of course, it's equivalent. And in fact, in the proof above, I did that. I did this in the proof of the previous corollary. So nothing to add there. Another one that pops right out, and these sound maybe kind of silly, but if r is bigger than 0, there is r is a real number again. So I'll say r and r plus. There is an n such that r lands in an interval. So let's see, such that n minus 1 is less than or equal to r, and that's less than or equal to n. Another way to write that is that r falls in the closed interval from n minus 1 to n. This is important. This means I can partition the real numbers into intervals. Something everybody does when they draw the number line, and they realize, okay, the integers are little tick marks along the real line, and any real number falls in one of them. It's like, duh. But once we know this, we don't have to think about it anymore. I guess it's fun to see how you would deduce this from the basic Archimedean property. Fun for me, at least. Let's see. So let's let S be the set of all integers, positive integers, such that m is bigger than r. Okay, that's, notice that it's not empty. So the Archimedean property implies S is not empty. So it has the smallest element. That is the well-ordering property. Well-ordering property of the natural numbers that we hit last week. Implies that there's a smallest element. It has a smallest element. Let's call it n naught. And that's the one we want. So let's see. That means n naught is the smallest one, and that means n naught minus 1 is not in S, because n naught is the smallest one. Let's see, n naught. And n naught minus 1 is not in S. It could be 0. If 1 was in S, then this would be 0. But whatever it is, it's not in S, because n naught is the smallest one. Okay, so that means that R is not, that means that, so n naught minus 1 is not greater than R, it's less than or, what? Yeah, n minus 1 is less than or equal to R. It's not bigger than R. Otherwise, it'd be in the set. And therefore, in fact, what we see here is that R is in n naught minus 1, and I proved that it was less than n naught. So it doesn't actually get in that set what I promised, and that set would be n naught minus 1 closed interval. Check. Anyway, that's nifty because it uses the well-ordering property to find this interval. It basically slides intervals over until you hit it. Questions about that or anything? Yeah. That's a subset. That half-open interval is a subset of the closed interval, and that's what it was in the statement of the theorem in the book. They demonstrated it in such a way that they got a little bit more than that. Yes, I mean, if R was if R was an integer, then it would be a left or a right endpoint. So that's kind of the case where you wouldn't care what would happen, because that's the obvious case. A funny fact: this Archimedean property and the corollaries are called the Archimedean properties of the real numbers. And so I have a colleague in the math department who studies non-Archimedean fields for a living. Hard to imagine. And there's some wild and crazy things that happen in non-Archimedean fields. I guess there's some obvious examples of non-Archimedean fields, namely finite fields, because then if you need infinitely many things to get big ends in the field, and if there's only finitely many, that's not so clear you can do that. In fact, you can't do that. But there's infinite non-Archimedean fields. So this whole area of math that my colleagues spent a lifetime studying, non-Archimedean fields. R is an Archimedean field. So it satisfies the field properties and these basic axioms that Archimedes realized were necessary. Well, something that's going to pop out from these considerations is important today, and it's the fact that the rational numbers are dense among the real numbers. So a consequence of the Archimedean property. Rational numbers are dense in R. I haven't told you what dense means, but I will. Meaning, give me two real numbers that are different, given R1 and R2 in R, with R1 less than R2, there's a rational number. To emphasize that it's rational, I'll write P over Q in Q, the rational numbers, that's between those two. So with R1 less than P over Q, less than R2. That's what it means to be dense. And if you think about it now, of course rational numbers are real numbers. Now there would be a rational number between P over Q and R2. And there'd be one between R1 and P over Q. And then there'd be ones between all those two. So in fact, there's infinitely many. That's not hard to see. Once you have one, then you just pick the other side and get one more in the middle there. Pick the left-hand side and get one in the middle there. And just keep doing that until you get infinitely many that are different. There are infinitely many. Okay, let's well, let's see. We demonstrated that the rational numbers are countable, and so this would be a subset. It'd be an infinite set that's a subset of a countable set, and it's a fact that such a set would have to be countable. Subsets of countable sets are countable. That's a fact. It's kind of a tricky proof. I could make you believe it by sort of yeah. I don't think I'll try to make. I mean, it's not hard. I could make you believe it in 10 minutes. But to write out a map that would do it would be you'd have to sit and think about it for a while. Yeah, this is a count. There's countably infinitely many. Oh, you should read the book's proof. I found the book's proof to be kind of formal. I need a picture proof to do these things. It's only 3 sentences, so it's not a killer proof, but somehow it didn't feel natural to me. Let's see. So here's my proof. Let's say let's say that R1 is less than L. Yeah, we got R1 less than R2, are real numbers. Then, so R1 is less than R2. So R2 minus R1 is positive. And so one of the corollaries above, second one I think, implies there exists an n in the natural numbers with 1 over n less than R2 minus R1. Okay. And so 1 would be less than n times R2 minus R1. And let's see, that's equal to n times R2 minus n times R1. Okay, so that's bigger than the length of a unit interval, of an interval between natural numbers, n and n plus 1. And so the other corollary, so now I'm thinking out loud here. I'm going to picture proof of this thing. My other corollary implies, let's see, so I'm going to apply the other corollary to n times R2. That n times R2 is in an interval. Let's see, the interval I had before was m minus 1 to m, but that's the same as m to m plus 1. For some m. Okay, now I'm going to draw a picture. I've got n times R2 here, and n times R1 is smaller, and this distance is bigger than 1. So if I go backwards, okay, so that this is this thing right here, m to m plus 1. So here's m plus 1. Right, because that red thing is bigger. I don't know if red does it. It's bigger than 1. And so even if I slid that little left-hand m all the way over, it would be in that red stuff. Because the length of that is greater than 1. So if I slid it all the way over, m would still be in there. Okay, and of course, if R2, so, so I get that R1, let's see, I have n times R1 is less than m to m plus 1. Am I messing this up? Okay, well, here's how people write proofs. They realize, oh, darn, I'm messing this up. Let's see, what I wish I had. Let me fix it. I'm going to put a 1 over 2 here. Then I would get 2. It's bigger, that thing is bigger than 2. And so now when I go back by 1, I'm definitely in there. So this would be m minus 1. Even if I slid m all the way over and made it equal to R2, that one would still be in there. Okay, there's a picture proof. Anything you can prove with a picture proof is true. So let's see. I get that 2 is less than that. That's good to know. And so I get that n times R1 is less than m minus 1 is less than n times R2. And therefore, R1 is less than m minus 1 over n. That's the P over Q I want, is less than R2. So I got you a rational number that's strictly in the middle there. So check. That's the end of it. Sorry for bumbling around there for a second. Funny thing, now that we know that there's rational numbers plastering all over everything, we can find out there's irrational numbers also plastering everything. Dense. So, irrational numbers are dense too. Meaning, given R1 less than R2, real numbers, there's an irrational number. What should I call irrational numbers? How about a Greek letter? C. Oh, C's are agony to draw. Tau. It's between the two. R1 is less than tau is less than R2. And the proof's a no-brainer. Once you think about it for a little while. Anybody got an idea how to do it? We only know one irrational number at the moment. Square root of 2 is going to somehow be involved. Pi is irrational, e is irrational, but at the moment we only know that square root of 2 is irrational. Ideas about what to do? Oh well, I don't have to do it. That would go back to sort of first principles. I can use something I already know. Yes, similar to that idea. Yeah, so if you think about things like that, like the homework problem with the s plus t times the square root of 2, here's the trick. R1's less than R2, so R1 over the square root of 2 is less than R2 over the square root of 2. And we know that there's a rational number between there. So there exists P over Q in the rationals with P over Q stuck in between those two things. And now I multiply by square root of 2 and see that R1 is less than P over Q times the square root of 2 is less than R2. And I claim that this is irrational because we know square root of 2 is irrational. Why is that irrational? Let's think about it. Square root of 2 is irrational. It turns out if you multiply irrational by irrational, it's got to be irrational. Also. So it's like 12 times pi is also irrational. And 2/3 of pi is also irrational. Yeah, let's see, if it was rational, then I could solve for the square root of 2. And I get that square root of 2 is rational. I guess I'll put a little quick demonstration in the margin here. P over Q, square root of 2, equals rational, then it would be equal to, oh, how about curly P over curly Q? That would imply square root of 2 is rational when you solve for it. And we know it's not, so that would be a contradiction. So I got you one in between there. And of course, when you get one, that means you get infinite, many, because I get another one between these two, one between these two, and then just keep plastering it. A fascinating fact is that you mentioned the rational numbers are countable, and the real numbers are uncountable. That means the irrationals are also uncountable. So there's lots more of them than there are rational. So it feels like it's a similar denseness, but these things are really dense. I guess there's a fancy word for what they are. They are a set of full measure. So if you measure them like in the sense of length, the irrational numbers would have the full length of an interval inside, and the rationals would be a set of measures 0. They don't cover any real length. Anyway, that's a much more advanced subject, and that's why the Lebesgue integral was invented, to study questions like that. Let's see, there's one more thing I need to do today to finish off this section. This is going to sound maybe silly after all the talking we've been doing, but this section shows us that the square root of 2 exists. The Dedekind cut business kind of inspired you to say, well, we know what the square root of 2 should be, and Dedekind took cuts and defined that to be the square root of 2. Of course, he proved square root of 2 exists from first principles. But now we have the least upper bound property, and that's kind of all we've got. I need to show that using the least upper bound property, that I can show that there's a number whose square is 2. Then we can stop worrying about it. Okay, and so in the page in the book, it's a full page. It's not hard, and I'm going to show you why that it's natural. But it's a full page you should read carefully. Let's let S, I'm not going to take rational numbers here today. Let's let capital S be the set of little s's in R plus such that S squared is less than 2. Okay. Previously, I took rational numbers like that. But now I'm taking all numbers like that, real numbers like that. It's clear that that's a bounded set from above. For example, if S was 3 or more, then S squared would be way more than 2, 9 and up. So S is bounded above by 3, for example, and even more by 4. And so it has a least upper bound. So it has a supremum, which is the same as a least upper bound. Let's let R, that's a real number, so let's let R be the sup of S. Okay, so here's what I'm thinking. I've got square root of 2 here, and I've got this set S. And I don't know if there is a thing whose square is 2 yet. I'm going to show you there is one. Okay, and so the R is the least upper bound. We're going to expect the R to actually be at the square root of 2. This is expected. Okay, so I've got this R. So let's do the case where R turns out to be less than the square root of 2. Let's see. I claim R squared equals the square root of 2. All right. Well, remember the trichotomy. Let's think trichotomy property. Give me two numbers. They're either equal, or one's bigger, or one's smaller. Let's do the case where R squared is less than the square root of 2. So let's do R squared less than the square root of 2. Let's think about that. That means I've got some wiggle room. So for example, if I took r plus 1 over n, something really tiny, and squared it, that would be equal to r squared plus 2r times 1 over n plus 1 over n squared. And maybe I can make that less than 2. R squared is less than 2. And this other stuff is really small. So in fact, I can pick the n big enough to make that other stuff really small and get a real number whose square is also less than 2. And that would mean that r is not a lower bound. There's one that's even bigger. I mean, it's not the greatest. Sorry, it's not the. Trying to get. You'll see what I'm going to get in a minute. So the thing I want to make this less than 2 minus r squared. Okay, so my picture is I've got 2 here. I've got my r squared, which is strictly less. And I want my r plus 1 squared to fall right here. R plus 1 over n squared. I want that to fall somewhere before 2. Okay. And so now I'm going to mess around. Notice that 1 over n squared is less than 1 over n for all n equal 1, 2, 3, etc. Okay, so that stuff there is 2r times 1 over n plus 1 over n squared is less than 2r times 1 over n times 1 over n plus 1 over n. And that's equal to 1 over n times 2r plus 1. And I want that to be less than 2 minus r squared. And so now when I write when I see what I need 1 over n times 2r plus 1 to be less than 2 minus r squared. Which means I need n to be bigger than what? And 2r plus 1 over 2 minus r squared. I can get an n by the Archimedean property. The Archimedean property. To get such a big n. And once I have a big n, I can go backwards. And I realize that I got something with a bigger thing that's stuck in there. Oh yeah. Let's see, I'm going to run out of time here. It's not enough. So I'm going to get a contradiction. And so it's not the case that r squared is less than 2. And so the last case I need to check is r squared bigger than 2. And it's very similar.